can you see my screen now?
Yes, sir.
Okay, all right. So in the last lecture, we talked about diagonalization, and then we realized that not every matrix is diagonalizable, or not every linear operator is diagonalizable. Then what can we do next? So the, then we saw that every complex matrix is not diagonalizable, but every complex matrix is upper triangularizable. That means you can always find an invertible matrix P such that P inverse AP is upper triangular. Similarly, for operators, you can answer that if T is a linear operator on a finite dimension vector space over C, then there exists a basis of the vector space with respect to which the matrix of T is upper triangular. And as I mentioned, that this is very useful result because using this you can you can answer many other questions. For example, you can say that you might have learned this earlier also in your graduation that product of eigenvalues is the determinant and sum of eigenvalues is the trace of the matrix, right? But this is now easily follows because of that result. So if somebody asks you how to prove that, then you can use that and you can easily prove, because if suppose A is a matrix of size n cross n over C, then you know that there exists a matrix P which is invertible such that P inverse AP is upper triangular. So it is this upper triangular. And you know that what are the entries here on the diagonal? They are nothing but the eigenvalues of A, because similar matrices, so let's call this T, upper triangular matrix. So A and T have the same eigenvalues. So, and for the upper triangular matrix, diagonal entries are the eigenvalues. So these are the eigenvalues of A here at the diagonal, right? Now, if you look at the determinant of A, which is same as determinant of PTP inverse, and now you can use the determinant rule. So it would be determinant of T, but determinant of T is just the product of these diagonal entries. So if you call them lambda 1 to lambda n at the diagonal, then it would be product of this lambda 1 to lambda n, which are the eigenvalues of A. So determinant of A is the product of eigenvalues. Similarly, you can prove that trace of A using the trace property the same way, and it would be sum of eigenvalues. This is one of the example, but there are many other questions you can answer using this important result. We will state another version of this result, which is actually called the Schur's lemma, where you can choose this P matrix as unitary matrix. So basically, you can say that every complex matrix of size n cross n is unitarily similar to an upper triangular matrix. That means instead of invertible matrix, you can actually choose a unitary matrix. So unitary matrices are also invertible. So in particular, you can choose unitary matrix such that P star AP is upper triangular. So we will see this result also, and this is the result which is used in computing the eigenvalues practically. Like the algorithm that uses uh, that computes the eigenvalue, that gives you the eigenvalues of a matrix numerically. That is the that algorithm uses this Schur's lemma heavily. So that is actually based on this Schur's lemma. Okay, so let us start after this diagonalization and triangularization. We can talk about like simultaneous diagonalizable. That means diagonalization. That means instead of one matrix, let us start with two matrices. Like let's say A and B are two given matrices of the same size. Then can we say like A and B are simultaneously diagonalizable? That means can we find a common matrix P invertible such that P inverse AP is diagonalizable as well as P inverse BP is diagonalizable? So the same matrix both the diagonalizes both A and B. Okay, so let me first give you this definition. So we quickly cover this simultaneous diagonalization and then we'll move on.
Hello, sir.
So yes,
यहाँ पे जैसे मैट्रिक्स थी वो ट्रायंगुलाइज थी, देन हम बात कर पाए कि डिटरमिनेंट जो होता है मल्टीप्लिकेशन ऑफ आइगन वैल्यूज होता है एंड ट्रेस होता है
हम्म,
सम ऑफ। बट सर अगर कोई मैट्रिक्स हो ट्रायंगुलाइज ना हो, देन सर क्या करेंगे? जैसे हमारे पास था 0 1 -1 मीन्स आर पे था वो।
0 1।
मीन्स अगर हम एम एन कॉस एन टू आर लेते हैं ना, तो हमें कभी कभी क्या होता है लैम्डा कॉम्प्लेक्स वैल्यू होती है, तो मतलब वो ट्रायंगुलाइज भी नहीं होता, ट्रायंगुलाइज भी नहीं होता
Yeah,
है,
so
तो
then you
वहां पे सर
cannot
कैसे
say na,
देखें?
because so then if the matrix is over R, then you cannot, like in general you cannot say that the determinant is the product of eigenvalues, because the matrix cannot have eigenvalues at all. Okay. So for
ओके।
example, the example you gave, this one, the rotation matrix, this example here, this matrix doesn't have any real eigenvalue. If you consider this matrix over the field R, then this matrix doesn't have any eigenvalue, but you can still compute the determinant, right? You can
यस
still
सर।
talk about the determinant, you can talk about the trace, but since it doesn't have any real eigenvalue, so you cannot say that this is this. Some determinant is the product, and trace is the sum. You cannot talk about that because it doesn't have any real eigenvalue. So this we can say, in general we can say only for complex matrices. But if the matrix has if the real matrix has real has an eigenvalue, then you can do this. So if you can say that if you know in advance that the matrix has matrix, so any matrix over R has let's say n eigenvalues, if it is of size n. If you know that it has n eigenvalues, then you can say that the trace is the sum of eigenvalues, and the determinant is the product of eigenvalues, because then you can use the same proof which you use to upper triangularize a given complex matrix. Because the main reason why this the same result doesn't work for real matrices, because real matrices doesn't have an eigenvalue. And if you recall the proof of this result, that every complex matrix is upper triangularizable, in that case we use the fact that this has every complex matrix has an eigenvalue, right? So using this actually, if suppose in advance you know that the matrix has n eigenvalues, then you can say that trace is the sum of eigenvalues, and determinant is the product of eigenvalues. Does it make sense?
यस सर। सर वन थिंग आल्सो, सर हाउ टू सर ट्रायंगुलाइज द मैट्रिक्स? मीन्स कोई मैट्रिक्स गिवन है, मतलब इसको अपर ट्रायंगुलर उनके सिमिलर कैसे दिखाएं? सर एक एग्जांपल।
You are saying that how to find this matrix P, right?
यस सर,
So
यस सर।
that P
सो
inverse
दैट पी
AP.
इनवर्स ए पी इज इक्वल टू अपर ट्रायंगुलर।
Yeah. So it is not it is possible, but it's not that straightforward. I mean, you cannot, like in general, say that for example, in case of the diagonalizable matrix, you can say that okay, this P is the, you can take P where the columns are nothing but the eigenvectors. But in case of this upper triangular matrix T, you cannot say that the columns of P are the eigenvectors eigenvectors of A. So in that case, it is not that easy to find this P, but there are numerical ways to find this P, such that P inverse AP is T. So this is actually, I think, how to do that. So um, I can give you some idea, but you need to see whether it works or not. So this, whatever I mentioned, that is an existence result, and it can be like one can find this matrix P. There is an algorithm. In case of Schur's lemma, you can actually find this matrix P, which is unitary, such that P inverse would be P star. So P star AP is upper triangular. So how to find this P basically is, so what is your aim? So you are given this matrix A. So let me give you some idea. So this idea works actually. This is the idea which is used in finding this matrix P. So what you have, so you have this matrix A. So let us call this A, this one. A11 to A1n, and then AN1 to ANn. Okay. Now what you want to make it upper triangular, right? So what you need to do, you need to produce zero. Let us start with the first row. So it is like it works in this way. How to find this p? So you try to make zero in the first column, right? After one entry, you want to make zero here, right, at this position. So you can do that. You can do that by using elementary matrices. You can multiply with the elementary matrices, let's say E1 to En minus 1 from left hand side to this A, such that this matrix A11, I mean, this is not the exact one, but this is the modified one, that it will have 0 in the first column, and the rest of the entries would be there. Modified entries would be there, but you don't know what are these entries. But you can actually ensure that in the first column, after the first entry, other entries are 0. This you can achieve by multiplying this, right? And now you also this is fine. Now this way you can actually, now further you can multiply with, let's say, um, a new set of elementary matrices that works on this submatrix here, right? And then again you do the same thing and create zeros here, like in the at this position, using the appropriate elementary matrices. That also you can do. So basically you can always create zeros such that this matrix at the end you have here, and these matrices here are the invertible matrices. The elementary matrices are invertible, so you can basically find a matrix E which is the product of elementary matrices such that EA is of this form. This you can do. So what you are doing, you are creating zeros here. That you can do. You have done this actually in while solving system of equation. But here you need to make sure that this you have to also multiply A from right hand side with E inverse. So that means you actually, so this is only one way. So you only get E such that EA is upper triangular. That you can do. But while doing this, since you keep in mind that you need this one, that P inverse AP is equal to T. So what you need to do, you need to somehow achieve this not only this way, but you have to do it in the process somewhere. Use the fact that you need to preserve the similarity transformation. That means you have to multiply the same matrix from right hand side also. Then only you can say that this matrix and the matrix here, they are similar if you multiply on from E inverse from right hand side. Otherwise they won't have same eigenvalues. Okay, so you need to like do something here while achieving the creating zeros here. You need to multiply from right hand side also, so that you still make zeros, create zeros in the matrix, and you also preserve the similarity transformation. That means eigenvalues. So this way, this is one way to create zeros. But as I mentioned that this is not a this is not what is used in practically in finding eigenvalue eigenvectors. Instead of P invertible, we look for a unitary matrix P. Instead of just invertible P, we ask for unitary P, such that P star AP is upper triangular. So as I mentioned, this is the result. This is known as Schur's lemma, and this result is practically used to find. So there you can find this matrix P by using by using similar idea that you want to create zeros, but you want to create zeros in the matrix in such a way that it also preserves the similarity transformation. Okay, so that is this one can achieve by introduce by choosing these matrices which are used to create zeros. Instead of these elementary matrices, one can use rotators and reflectors. So I don't want to use these terms because we have not talked about, but these are rotators and reflectors. They are kind of matrices. They are unitary matrices that satisfy certain properties, and they can be used to create zeros in a matrix. So this P matrix is actually a combination or a product of certain rotators and reflector that that is actually used to create zeros or to transform A into an upper triangular matrix. Okay, so this is the idea that one can use sort of elementary matrices, but elementary matrices are not unitary, so there you there it is used rotators and reflectors to create zeros in a matrix. So it is possible to find this, but it is not that straightforward. It's like it would be difficult for you to do using pen and paper. If the matrix is, let's say, even 3 by 3, it would be difficult for you. A lot of computations, but there are algorithms that gives you this factor p. Okay, is it okay?
Okay, sir.
Yeah, you can explore this. You can Google it and you can explore. But this is the idea. Okay, all right. So I was talking about simultaneous diagonalization. So let me define this first. So we are left with after this we will be left with two more lectures. So I want to cover at least a few more things. This is just because when you go for interviews, let's say after MSc, if you go for PhD interviews, these are some basic things which is like which you are supposed to know. So that's why I want to cover these basic things at least. Let us touch them, if not in detail, at least explain the definitions and give some problems so that you can actually make yourself familiar with these kind of topics also. Okay, so there are 2 3 more topics after this I would like to cover. Okay,
Sir,
yeah.
sir, you said that you will take 2 classes on applications. Sir,
Yes, so actually, I would like to. I actually have prepared my lectures also. 2 lectures I have prepared for. I mean, lecture slides I have prepared for applications, but unfortunately, we are going very slow. So I'm very slow in explaining things, and uh, like we are like we don't have much time to do that. So what I can do is that if you are still interested, I can take 2 extra lectures just for the application part, where I also want to tell you that why these topics are so important and why they are of practical use. I always mention that I will take, and I also would like to take at least 1 or 2 lectures on application, but we don't have much time. We have 2 more lectures after this, and I still need to cover some basic things which you are supposed to know after masters. So what we can do is that if you are still interested, I can take 2 lectures, if not two, then at least 1 lecture, and give you some application of the topics which we have learned in this course. Okay, so you discuss among yourself and suggest me some time after Diwali. I can take, let's say, 1 hour or 1.5 hour lecture to show you some application at least, that why these topics are important. Okay, but 2 lectures, I mean the scheduled lecture, I don't want to take application part in those lectures because there are some important topics which I would like to introduce. But I can take like extra class, maybe one, if not two, and I can explain a few things related to application. All right.
okay, sir.
So just let me know. You discuss among yourself and let me know if you want this class, and then I can do it after Diwali, the week after Diwali. Anytime, any day is fine. Just tell me some free common time for you. Okay, so let us move on. Simultaneous diagonalization. So what is this? So as I mentioned that instead of starting with a matrix, you start with 2 matrices, let's say A and B. Both are of size n cross n, of the same size, over F, let's say, not over C, over F, where F is either R or C. Then we say that then we say that A and B are uh, simultaneously diagonalizable if there exists an invertible matrix, let's say P, such that P of the same size over the same field, invertible matrix P, such that P inverse AP and P inverse BP both are diagonal. Are both diagonal. Okay. So that means the same matrix P diagonalizes A and B. Now one thing is very straightforward. You can see that you can see this as a necessary condition. That means let me write this as an observation. You can make this observation. So if A and B are let's say A and B are simultaneously diagonalizable. So you can see that if A and B are simultaneously diagonalizable, and suppose that they are simultaneously diagonalizable, then you can easily verify that. Then you can see that A and B both commute. A and B both commute. So if A and B are simultaneously diagonalizable, then A and B both commute. So this is not difficult to see. It's very easy to see. Because A and B are simultaneously diagonalizable, then you know that there exists P invertible, such that P inverse AP and P inverse BP both diagonal, right? So they are both diagonal. Now what you want to see, you want to show that AB is equal to BA, but that is not difficult because AB, what is AB? A you can see, okay, so A, P inverse AP and P inverse BP, they are diagonal matrices, and you know that if A and B are diagonal matrices, if you have two diagonal matrices, then diagonal matrices always commute. Okay, so P inverse AP and P inverse BP both are diagonal, so they commute. So what you can, instead of rewriting this, you can look at it in this way, that P inverse AP and P inverse BP, they commute. That means this is equal to P inverse BP and P inverse AP. Because they are diagonal, so they commute. But then this is equal to like P inverse ABP equal to P inverse BAP. But then again you can multiply with P from left hand side and P inverse from right hand side. So this implies that AB is equal to P. So that means if A and B are simultaneously diagonalizable, then A and B both commute. Now what about the converse? So is the converse also true? Okay. So what about the converse? What do you say? What do you think? At least what is your guess? Is the converse true? If what would be the converse if A and B are, yeah, the converse is, what would be the converse if A and B are two matrices such that they commute? Does it imply that they are simultaneously diagonalizable?
सर
So what
अगर
is
A और B
Converse is true.
diagonalizable,
Yes, sir, true.
converse is also true?
सर अगर
What
A और B
difference है?
diagonalizable है तो
A and B are diagonalizable है तो, otherwise in general,
in general true नहीं है
can you give an example? So one of you said that it is true. Converse is true.
फॉलो करे प्रूफ तो ट्रू हो जाएगा.
आवाज नहीं आ रही है आपकी ठीक से.
सर जो प्रूफ हमने ऊपर किया उसके सेम स्टेप्स फॉलो करें पीछे से तो वो ट्रू हो जाएगा हर चीज.
कैसे होगा? Let us check. Your voice is not clear, but I understand what you are saying. So you are saying that let us follow from here to here. So this direction, let's see. So okay, so let us suppose that A and B are two matrices such that AB is equal to BA. That is fine. Now, how to get from here to one step above? How to get this? How do you find? How do you know that there exists such a P? Or you can multiply with any invertible P. That also you can do. So if you just take any invertible matrix P, then from here to here you can come. Then from here to here also you can come. But then how do you know that P inverse AP and P inverse VP both are diagonal? Up to this is fine. You can come from here to here with any invertible matrix P. But the thing is that how do you know from here that P inverse AP and P inverse VP, they are diagonal if you choose any P? So in general, this is not
not
true. Yeah, you can take like easy example. Let's say this is A and this is your identity matrix. You know that this matrix is not invertible. A matrix is not diagonalizable. A matrix is not diagonalizable, and B is a identity matrix, so it is always diagonalizable. If you look at AB equal to BA, then this is true for any A. So in particular, I have taken this A. Now clearly A and B are not diagonalizable because this A matrix is not diagonalizable. So A and B cannot be simultaneously diagonalizable. So but A, B are not simultaneously diagonalizable. Why? Because as A is not even diagonalizable. So therefore, you can directly cannot say that the converse is true, but if you add something extra, like you can see that this matrix A is not diagonalizable, but B is diagonalizable in this example. So if you assume that if A and B both are diagonalizable and they commute, then this implies that A and B are simultaneously diagonalizable. This is true. This is true. This we will see how to prove. But so in order to prove this, or in order to achieve this proof, I need this lemma. So I will prove this, that if A and B are diagonalizable and commute, then this implies that they are simultaneously diagonalizable. Okay, but before this, let me prove this result. So suppose that we have a matrix A which is of size n cross n over, let's say, C, and B is of size m cross m over C. Then let us call this matrix capital X, which is a block diagonal matrix where at the diagonal we have blocks A and B. So this is of size n plus m cross n plus m. So zero matrices these zero blocks are of appropriate size, so that this X becomes n plus m cross n plus m. Then this X is diagonalizable. X is diagonalizable if and only if both A and B are diagonalizable. So this looks very like at least we can guess that okay, this is true, that if X is of this form, then we can say that if X is diagonalizable, then A and B are diagonalizable, and the other side is also true. So let's see why this is true. So we have to prove both the direction. It is a if and only if result. So let us prove the only if direction first. So suppose that A and B are both diagonalizable. Okay. So A and let A and B are A and B be diagonalizable. A and B be diagonalizable. Okay. Now using this, we have to prove that X is diagonalizable, right? So that means we need to find a matrix P of size n plus m cross n plus m invertible such that P inverse XP is is diagonal. Okay. Now what we are given? We are given that A and B are diagonalizable. If A and B are diagonalizable, then what can we say? So we need to find an invertible matrix for X such that this X becomes diagonalizable. Now can you tell me what should I do next? I'm given that A and B are diagonalizable.
Exist a matrix P and a matrix Q for B.
Hmm. Okay. Yeah. So this implies that there exists invertible P of size n cross n and Q of size m cross m, both are invertible, such that P inverse AP is diagonal. So let us call this diagonal matrix as D1, and P inverse, oh sorry, Q inverse BQ is also diagonal. So let us call this D2. Okay. So these are diagonal. D1, D2 are diagonal matrices. Now what we have to show? Our claim is to show that this X is diagonalizable, right? This is diagonalizable. This we have to show. So we have to find a matrix. Let's say some matrix, whatever you call this matrix. So let us call this matrix Y. We need to find a matrix Y of size n plus m cross n plus m such that Y inverse XY is diagonal. So can you tell me what should I choose for this Y?
P0 0 Q.
So you are saying P0 0 Q. Now
Yes, sir.
why this matrix? So this is clearly of size n plus m cross n plus m. This is fine. Why this is invertible?
Because P and
Why
Q are integral.
so?
So the column vectors are linearly independent.
Yeah,
That's why.
so column, yeah, yeah, that is also fine. You can also find the determinant of y, which is the product of determinant of p and determinant of q. Yeah, that is also fine. Anyway, so this implies that y is invertible. And what would be the inverse of y? Can you tell me? We need to compute y inverse also, no? Y inverse x y. So what is y inverse?
Q inverse
Plus Q
0
zero
0
zero
P
P.
plus.
Yeah, p inverse 0 0 q inverse. So this is y inverse. Now you can verify why this is y inverse because y inverse y equal to y inverse is equal to identity of size n plus n. Now also look at y inverse xy, what it is. If you do this, then it is y inverse is p inverse 0 0 q inverse, x is a 0 0 b, then we have y p 0 0 q. When you multiply this, you will get p inverse ap 0 0 p inverse q inverse bq, and this you know what it is, it's d1 0 0 d2. So d1 d2 are diagonal, so this is also diagonal. So this proves that, so this implies x is diagonal easy. So one side is relatively easy. Okay, now how about the converse, the if direction? So we have proved only if, so we have to prove. So that means let us suppose that, so conversely, let x is of this form is diagonalizable. Okay, so using this we have to show that a and b are diagonalizable, right? Now x is diagonalizable, so what we can say, we can say that there exists p of appropriate size, invertible, uh, invertible, such that p inverse xp is is diagonal, and this diagonal matrix is of size n plus m cross n plus m, right? And let us call these diagonal entries as, let's say, lambda 1 to first lambda n, and then lambda n plus 1 to lambda m. Some of these lambda i's may be repeated, but let us call these diagonal entries this. We don't care whether they are distinct or not. So the diagonal entries I am denoting from lambda 1 to by lambda 1 to lambda n plus n. Okay. Now what we can see from here, if I denote, let's say, why I have written it in this way, if I denote P matrix as, so P is the matrix of size n plus m cross n plus m. So if I denote P matrix as column wise, let's say x1, x2, and up to xn plus m, where these xj, for each j, this xj is of size n plus m cross 1. So it's a column vector of size n plus m. So I'm denoting this xj also like let's say alpha j, beta j, where alpha j is of size n and beta j is of size m for each j. Okay, is it fine? Can I do that? Is there any doubt? Can I do it in this way?
Yes, sir.
Yeah, so there is nothing special. I've just written P column wise, and each column is of size n plus m. So the first n component I'm writing as alpha j, and the last m minus n components I'm writing as, last m components I'm writing as bj for each j. Now since P inverse, we know that P inverse xp is equal to D. So if I call this as a D matrix, then this implies that xp is equal to pd. But then this implies that x small xj is equal to lambda j xj for each j, right? Because this column vector, these columns of P are nothing but the eigenvectors of x. Now this implies again, I can write xj as alpha j beta j, and this would be lambda j alpha j lambda j beta j. So what we can say from here, if you now look at what is this x also I can write as in the block wise, x matrix is this one. So what I can say from here, it is A alpha j is equal to lambda j alpha j, and B beta j is equal to lambda j beta j. So now what I can say from here, I can say that this alpha j, I can see some can I say something here, something from this? What do you see from this expressions?
Alpha j is eigenvalues for A.
Alpha j's are eigenvectors.
Sorry, हाँ.
I mean,
Lambda
they
j is
could be
Lambda j.
eigenvectors. Yeah, lambda j's are eigenvalues, and alpha j could be eigenvectors, provided they are non-zero. Similarly for beta j. So if they become like non-zero, then we can find, if suppose these alpha j's are non-zero, then we get eigenvectors corresponding to lambda j. And if we show that these all these alpha 1 to alpha n here and beta 1 to beta n here, they are linearly independent, then we are done, right? Because then we find n linearly independent eigenvectors for this A, and B linearly and m linearly and independent eigenvectors for B, and then using the result which we have done in the last class, we can show that we can say A is diagonalizable and B is diagonalizable, right? So now consider this. So now consider this. Let's say alpha 1, alpha 2, and so on to alpha n plus n. So these are n. What would be the size of this? It is n cross n plus n. And also consider this matrix beta 1, beta 2, and so on to beta n plus m. And it is of size m cross n plus m. Okay. Now, what would be the rank of, let's say, this matrix here? Can you say something about the rank of this matrix and rank of this matrix?
At most n and at most m.
Can you say more than that? Can you say exactly n or exactly m? Because this is what we are interested in. If we can say that the rank of this matrix is exactly n, then we can say, okay, this is a full column matrix, then that means these alpha i's are linearly independent. Similarly for this also. Similarly for this
Yes, sir.
also, if we can we say that it's exactly n?
Yes, sir.
Why?
Because we consider xj are linearly independent.
Hmm.
तो xj को split करा था अल्फा j और बीटा j में, तो they are also linearly independent.
Yeah,
That's
so it is because of that, right? So since we know that P is invertible, P is invertible, this implies rank of P is n plus m. This is very clear, right? Because P is invertible. And this implies that rank of this matrix alpha 1 to alpha n plus m is n, and rank of this matrix beta 1 to beta n plus m, this is m. Why this is? Because, or if you look at P matrix carefully, what is this P matrix? P matrix is this one, alpha 1 to alpha n plus m, then beta 1 to beta n plus m. Okay. So the first column is alpha 1 beta 1, the second column is alpha 2 beta 2, and so on. And this is of size n plus m cross n plus m. Now this P matrix is of full column full rank, that means n plus m. So this matrix containing alpha is, this has to be of rank n, and the matrix containing beta j, this has to be of rank n. This is because of this. Now since we found a complete set of eigenvectors, so clearly we can say that the columns here, they are linearly independent. So therefore they form a complete set of eigenvectors for A, and similarly columns here. So yeah, so sorry, not linearly independent, sorry, I made a mistake here. So this is rank, this is of rank n. So what we can say that out of this n plus m columns, we can find, because rank of this is n, so column rank is same as row rank, so the column rank is also n. So that means, and there are n plus m columns, so what we can say, we can find out of these n plus m columns, we can find n columns which are linearly independent. Out of this n plus m alpha j's, we can find n columns, n alpha i's, which are linearly independent. Similarly for these beta j's, we can find m beta j's which are linearly independent out of this n plus m beta j's, right? And they form a like linearly independent, sorry, what did I do? uh, there was some, hello, can you hear me guys?
yes, sir.
Yes, sir.
Okay, so there was some error in my this app, so let me rewrite this thing again. So what I was saying is that out of this n plus m alpha j's, n, at least n alpha j's are linearly independent, not n exactly n, not at least, exactly n alpha j's are linearly independent. Similarly, m beta j's are linearly independent, and therefore we can find a complete set of eigenvectors for A, and similarly for complete set of eigenvectors for B, and therefore we can say A and B are diagonally zero. So rank of, since rank of alpha 1 to alpha n plus m is n, and rank of beta 1 to beta n plus m this is M. This implies thus choose alpha, let's say k1 to alpha. I don't know which alpha is are linearly independent, but what I can say is that out of this n plus m alpha j's, I can always find n alpha j's which are linearly independent. So I'm denoting them alpha k1 to alpha kn. This is just some index. Okay, this k1 to kn, they are some indices. So I can find this alpha k1 to alpha kn linearly independent from this alpha 1 to alpha n plus m. And similarly, let's say beta um, r1 to beta rm linearly independent from this set beta 1 to beta n plus m. Okay, then if I set, let's say, q1 as this alpha k1 and so on up to alpha kn, now this is n cross n, and let's say q2 as beta r1 to beta rm, then this is m cross m. Since columns of q1 are the linearly independent eigenvectors of A and columns of q2 are linearly independent eigenvectors of B, so this implies that q1 inverse A q1 is diagonal and q2 inverse B q2 is both diagonal, are both diagonal, and therefore you can say that A and B are diagonalizable. Okay, now I proved this result for two matrices, but you can extend this result and you can prove this for, let's say, any number of blocks at the diagonal of x. So let me give you this as an exercise. This, the same proof you can expand or you can extend uh, for this. So let us suppose that x is of this form a1 and so on up to ak. Let's say it has k blocks where k is greater than 2. X is diagonalizable. Assume that these diagonal blocks are all square matrices. Okay, if and only if AI is diagonalizable for each I. Okay, and you can try to prove this by induction. So let me give you some hint. So you can try to prove this by induction. This is easy to prove using induction because you can use the fact that for two matrices you have proved this. Okay, now we prove the converse of the statement which we asked at the beginning. So let me write this as a result. So what is that? Let A and B are two matrices of size n over the field F, or let's say over the field C also you can do, but for F also it is fine. Okay, we are not using anything for it's basically from C. So you can do it for F also, but since the previous result I proved for C, so let me also keep this as C. But you can just write F and everything is fine. Such that A and B are both diagonalizable. They are both diagonalizable. And also assume that they commute. Now using this, you have to show that then A and B are simultaneously diagonalizable. Okay, so let us prove this. How to prove this one? So what we are given? We are given that A is diagonalizable. A is diagonalizable. So this implies what? This implies there exists P invertible such that P inverse AP is diagonal. So this is diagonal, right? Similarly, we are given B is diagonalizable. So this implies there exists Q such that Q inverse BQ is diagonal. So let us call it D2. Right? Now P inverse AP, and so now what I want to show that A and B are simultaneously diagonalizable. That means I need to find a common invertible matrix, let's say X, such that P inverse AP, sorry, I have to find a common invertible matrix, let's say P hat, such that P hat inverse AP is diagonal as well as P hat inverse BP is diagonal. So the same matrix should diagonalize both A and B. Okay. So this is my aim to find this matrix. So for this, let me set X as P inverse AP. So then clearly X is diagonal. So it is actually the D1 matrix only, but I'm denoting it by X. So it's a diagonal matrix X. And let me set Y also as P inverse BP. So this Y is not diagonal. I want such a P that this P inverse AP and P inverse BP both are diagonal. But using this P here, I can only say that this matrix is diagonal, but Y may not be diagonal, right? But can you say Y is diagonalizable? Is this
Yes,
matrix
sir.
Y diagonalizable? Why?
Sir, because they are similar matrix.
They are
Similar
Y,
matrix.
yeah, Y and P, they are similar matrices, so they are right. You can use that. So what you can see here is that Y is diagonalizable. X is diagonal and Y is diagonalizable. So X is diagonal, but Y is diagonalizable. Y may not be diagonal, but it is diagonalizable. This is what we have. And also what we know that XY is equal, we know AB is equal to BA. Right? That means A and B commute. But what about XY? So let's see whether XY also commute. So XY, X is P inverse AP, Y is P inverse BP. So it would be P inverse ABP, but then AB commute, so it is P inverse BAP, but then again you can write it as P inverse BP, P inverse AP. So that means it is equal to YX. So what we have the following. From above, we have that X, which is P inverse AP, diagonal. We have Y, which is P inverse BP, diagonalizable. And we have that X and Y both commute. This is what we have, right? If this is the case, can you say what kind of this Y could be?
Y is also diagonal.
Y is also diagonal.
Yes, sir.
Are you sure?
So because of previous result, actually, आपको last class
But
में
there,
भी
yeah, yes,
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 sir.
yeah, I remember. That's why I have written it in this way. But that result says something extra. If you
Sir,
look
for
little.
sir, distinct diagonal entries on.
Yes. So if X has distinct eigenentries, that means the diagonal matrix, if the diagonal entries are all distinct, then you can say Y is diagonal. Y is also diagonal. But here, this may not be the case. We don't know. X can still be diagonal, but without having distinct entries at the diagonal. We don't know that yet. I mean, we have not assumed anything on this. So what else we can say? If not exactly diagonal, what can you say about Y? if you use the same idea, exactly the same proof, if you use, that means you just multiply x, y here and compare both the sides, you will see that y is not diagonal, exactly diagonal, but it is block diagonal. That means at the diagonal you will have some blocks like this, and other entries here 0. So that means what I'm saying is that you can verify if y, you assume that y is like having entries yij, and let's say x is diagonal, so it is of size n cross n, so at the diagonal it has lambda 1 to lambda n. But these lambda i's, if they are all distinct, then you can say y is diagonal, but this diagonal entries lambda 1 to lambda n, they may not be distinct. So where this lambda j's need not be distinct, right? Here we have not assumed, so they need not be distinct. But what you can say that the same eigenvalues are together, that you can say. So you can assume that this in the x, all the same eigenvalues, that means the same diagonal entries are together, that you can assume. So distinct and need not be distinct, and same uh, values are together, diagonal entries are together, or same eigenvalues, because diagonal entries are the eigenvalues, same eigenvalues are together. Together means that means you can say that the x is of this form. First lambda 1 is appearing, let's say if it is appearing r1 times, or let's say what notation we have not used, yeah, r1 times, let's say this is appearing r1 times, then you have lambda 2, this is appearing, let's say r2 times, and so on, and this is, let's say lambda k, that is appearing rk times, where if you add r1 r2 and so on up to rk, then it should be equal to n. Okay, so some of them are repeating. I'm saying that let's say lambda 1 is repeating r1 times and so on, and lambda k, so lambda 1 to lambda k, they are distinct, but lambda 1 is repeating r1 time, lambda 2 is repeating r2 time, and so on. Now if you multiply x, y, so here if you multiply with this thing, if you compare both the side, then what you will see, you will see that, so now since xy is equal to yx, this implies, you can check that this will implies that lambda I yij is equal to lambda j yij, but then this implies lambda I minus lambda j yij is equal to 0. So whenever lambda I and lambda j, they are distinct, this implies that yij is equal to 0 for all ij such that lambda I is not equal to lambda j. So that means this y has the form of this. So it would be of the form a1, a2, and so on up to ak. ak is, so this is your y. So y is of this form, this is of n cross n, where a1 is of size r1 cross r1, a2 is of size r2 cross r2, and so on. So ai is a matrix of size ri cross ri. Okay, so or you can say, so let me write it in most precisely, you can write that where these ais, they their matrix corresponding, ais is a matrix, for each I, ai is a matrix corresponding to distinct eigenvalues of distinct eigenvalues, let's say lambda I. So lambda, where ai is a matrix corresponding to distinct eigenvalue lambda I of size equal to algebraic multiplicity of lambda I. So how many times this lambda is appearing on the diagonal, that would be the size, that means ri. So since y is diagonalizable, right? This y, if you look at this, y is diagonalizable here. X is diagonal, but y is diagonalizable. If y is diagonalizable, what can you say? What can you say? If y is diagonalizable?
Y is similar to a diagonal matrix.
Yes. So what else?
A1 A2
Yes,
just
all
take
these
a
AIs
diagonal
are
matrix.
diagonalizable. Yeah. So because of this exercise which I gave you, if X is diagonalizable, if and only if X is diagonalizable, if and only if all these AIs are diagonalizable, and therefore you can say since Y is diagonalizable, this implies that AI is diagonalizable for each I. So what does it mean? That means there exists QI for each I such that QI inverse AI QI is AI inverse AI QI is diagonal, because each of them is diagonalizable, so you can find such a QI for each I. So now let us consider this Q. Let me see if we have not used Q somewhere. Whether we have used, yeah, we have used Q. So instead of Q, let me use something else. Let's say Z. So let us consider this Z matrix, or let's say maybe not Z, but Q tilde. So what is this Q tilde? Q tilde is a matrix where at the diagonal we have Q1 to Qk. So then clearly this, when you do this Q tilde inverse YQ tilde, then it is Q1 inverse and so on Qk inverse. Then Y is A1 to AK, and then Q tilde is Q1 to Qk. So clearly this is diagonal, right? So now when you multiply these, because each of Qi inverse AI Qi is diagonal, so this matrix is diagonal. What about this one, Q tilde X Q tilde? What is this? So let us see what is this. Q tilde inverse. Q tilde inverse is Q1 inverse, Q2 inverse, and so on, Qk inverse. Now X is what? Now look at X. X is here. So what you can say, X is lambda 1, lambda 1, then lambda 2 appearing R2 times, and so on, lambda k appearing Rk times. So basically what you can say that here is a block, and here is a block, and then here is a block, and so on. Sorry, here is a block. So sorry. So here Q1 to Qk. Now when you multiply this, what do you get? So can you tell me what do you get from here? When you multiply, what do you get? What would be the first block of this multiplication?
Lambda 1 I.
Lambda 1 Q1 inverse Q1, which is I. Then lambda 2 Q2 inverse Q2, and so on, lambda k Qk inverse Qk. So basically it is the same as, so this also is a diagonal matrix, right? This is also diagonal. So what we get Q tilde such that Q tilde simultaneously diagonalizes both X and Y, right? So now if you look at what is X, what is Y, so Q tilde inverse, X is Y is what? Y is P inverse BP, and X is P inverse AP. So let's see what it is. So Y is P inverse BP Q tilde, and similar. So this is diagonal because this is now you can write as it's the same thing, right? We have seen that q tilde inverse y q tilde is diagonal. So this matrix is diagonal. This matrix is diagonal. But what is this? This is actually you can write it as p q tilde inverse b p q tilde. And similarly, this matrix q tilde inverse P inverse A P Q tilde. This matrix is X. So this also we have seen that Q tilde inverse X Q tilde is diagonal. So this is also diagonal. But what is this? This is again same way P Q tilde inverse A P Q tilde. So both these matrices are diagonalizable. Both these matrices are diagonal. And here, since P is invertible, Q tilde is invertible, their product is invertible, and therefore you have found the same matrix. You can call this matrix, let's say some Z matrix, such that Z inverse B Z is diagonal and Z inverse A Z is diagonal. So from here you can see that A and B are simultaneously diagonalizable. Okay, and this completes the proof. So if A and B are two matrices, then you can say that they are simultaneously diagonalizable if and only if they are diagonalizable and they commute. Okay, so I will give some problems based on this simultaneous diagonalization. What I would like to introduce next is some kind of matrices, particular matrices like unitary matrix, normal matrices, Hermitian, positive definite, positive semi-definite. So in the next two lectures, I want to focus on these matrices because they are of a lot of use. Okay, so let us start with the unitary matrix. We have already defined but not discussed much about unitary matrices. So let us. So now onwards, I will completely focus on for next 2-3 lectures. I will completely focus uh, on matrices instead of operators, but similar results exactly in the same way you can obtain for operators also. But now I will focus only on matrices for the next 2 lectures. So unitary matrix. So what is a unitary matrix? Let me define it again. A matrix U of size n cross n over C is said to be unitary if U star U is identity. Okay, and in addition, if U is real instead of complex matrix, so if U is over the field R such that U transpose U is identity, then U is called orthogonal, or you can say real orthogonal, same real ortho. All right. Now there are several equivalent conditions for a matrix to be unitary. So I will write these conditions, but these conditions are not difficult to check. So you can verify yourself. I will just state them. They are very easy to check. So let me write this as a result. So if U is an n cross n matrix over C, then the following are equivalent. Okay, this TFAE means the following are equivalent. So what are these following? First one is U is unitary. Saying that U is unitary is equivalent to saying that U is non-singular, that means invertible. Non-singular or invertible. It's an n cross n matrix, so both are same thing. U is non-singular or invertible, and the inverse of U is nothing but U star. is invertible, and inverse is just the star is the complex conjugate transpose. C is, in the definition we said U star U is identity, so but it is also same as U star is identity. This is also equivalent. But then this C is saying the same thing, saying that U star is unitary. So all these things are equivalent. Not only this, using the fact that U is unitary and the property that U star U is identity, one can show that the columns are, one can show that this is equivalent to the fact that the columns of U are orthonormal, or you can say the columns of U form an orthonormal set. Orthonormal, if I'm saying orthonormal, that means I'm talking about an inner product. So the inner product is the standard inner product on Cn. Okay, and F is the rows of U, because U is unitary. It says that the columns of U form an orthonormal set, but U is unitary equivalent to saying that U star is unitary, and for U star it would be the rows of U. So you can say the same way that the rows of U form an orthonormal set. So all these we will derive some more conditions, but you can say from here that at least it is very easy to check that these 6 conditions are equivalent, and therefore I'm not going to prove this. I'm leaving this as an exercise. Okay, these are very easy to check, these conditions. There are 2 more conditions which I will prove, but at least these 6 conditions are very easy to check, and you can do it yourself. Okay, so sorry. Now you can also check not only this, you can also give one more condition. This also very easy to check. So let me do it here. You can also take this as an exercise, because these are very easy results to check. That let U be an n cross n matrix over C, then you can check that then U is unitary. It gives another condition, equivalent condition, to say U is unitary. So then U is unitary if and only if for every orthonormal set x1 to xn, or let's say x1 to xk, every orthonormal set in Cn, this set ux1, ux2, uxk, that means this is the product of u and x1, product of u and x2, and so on. This is also an orthonormal set in Cn. So for every, if U is unitary, then every orthonormal set, for every orthonormal set x1 to xk, ux1 to uxk, this is also orthonormal, and the converse is also true. That means if for every orthonormal set x1 to xk, if this set is orthonormal, then using this you can prove that U is unitary. So how to show this? So it's very easy to prove. Let me give you some hint. So this is if and only if, so you have to check both the directions. The if direction is just one line. What is given? Given that U is unitary. And what you have to check? You have to check that this is orthonormal if x1 to xk is orthonormal, is given. Okay, so assume that x1, so let x1 to xk, this is any orthonormal set in Cn, and you have to check that ux1 to uxk is orthonormal. So you just see what is this uxi star uxj. If this is equal to del ij, that means it is equal to 1 when I equal to j, and 0 if I is not equal to j, then you are done. So what it is actually xi star u star u xj, but u is unitary. So this implies u star u is identity. So it is xi star xj. But xi and xj, they form an orthonormal set. So this is equal to del ij. That means it is 1 when I equal to j and 0 if I is not equal to j. So clearly this set is orthonormal. That means ux1 to uxk is orthonormal. Conversely, conversely, if suppose for any orthonormal set x1 to xk, this is also orthonormal. This is given to us. Using this, we have to show that u is orthonormal. Now, how can we do that? So this is true for what is given is that every orthonormal set x1 to xk implies that this is also orthonormal. So in particular, if I choose a particular kind of orthonormal set, then I can say something about this one. Using this, I can say that this is unitary. So can you tell me what I should choose? What kind of orthonormal set I should choose here to show that U is unitary?
U as a column of ux1, ux2 dot uxk.
Okay, then, but you don't know whether, so you
Then
have to,
then
if you want, just a minute. So you have to use this given that for every x1 to xk orthonormal, ux1 to uxk is also orthonormal. Using this, you have to show that U is unitary. Now, if you start by taking columns of U as x1 to xk, then you don't know whether they are orthonormal or not. You have to prove that they are orthonormal in order to show that U is unitary, because it is equivalent to saying that columns of U are orthonormal. Anything else?
So standard basis E1, E2, E3 we can say.
Yeah, so if you take, let's say, E1 to En, then you know that this set is orthonormal. So this is clearly orthonormal set in Cn with respect to the standard inner product. And by the given hypothesis, this implies that UE1 up to UEN, this is also orthonormal because of the hypothesis. But what is this UE1 to UEN?
Columns of
They are the
U.
columns of U. So they are the columns of U. That means columns of U form an orthonormal set. And this is one of the equivalent condition, if you look at here, to say that U is unitary. So this implies columns of U form an orthonormal set. So, and you are done. So you see here, this gives another condition to check whether a given matrix is unitary or not. All right. So as I mentioned at the beginning that every matrix, every complex matrix is similar to an upper triangular matrix. But you can say more than that, that this matrix P, that upper triangularize A, that matrix can be chosen as a unitary matrix. So, and if this is the case, then this P, instead of saying that A is similar to P upper triangular, we say A is unitary similar to upper triangular. That means this similarity matrix P can be chosen as unitary. So let me define this first. What is unitary similar? Unitary similar, or we also use sometime unitary equivalent. So a matrix is very close to similar matrices. The only thing is that we also have unitary in this extra property on the matrix P. So a matrix B, let's say, of size n cross n over C is said to be unitary similar or unitary equivalent to a given matrix A of the size of same size n cross n if there exists a unitary matrix U the same size such that B is equal to U star AU. So you see here U is invertible, U is unitary, so U star is actually equal to U inverse. So it's actually similar to A is similar to B, but instead of saying similar, we are saying unitary similar because this matrix here is unitary. So it's, you can say it's similar, but it's unitary similar. So if A, if there exists a unitary matrix U such that U star AU is equal to B, then we say that A and B are unitary similar. So you see here, whatever properties similar matrices enjoy, the same properties are also enjoyed by unitary similar matrices. Not only that, in addition to that, we also have something extra because now they are similar, not only similar, they are unitary similar. So you can also take advantage of the fact that U is unitary. So what we have seen, so if I recall, let me recall uh, what we have done. What we know is that if A is n cross n over C, then there exist, there always, you can always find P invertible such that P inverse AP is upper triangular, right? This we have seen. That means every complex matrix, square matrix, is similar to an upper triangular matrix. Now, in the next result, I will show that the same thing you can achieve by unitary matrix. So next we show that, a similar result, and this result is very important in numerical linear algebra. A similar result is true with a unitary P. So this P is not only invertible, you can choose P as a unitary matrix and you can achieve same thing. This result is known as Schur's lemma. And as I mentioned that, let me just state this result first and then I'll tell you the advantage of this result. We will prove this in the next class. So let me just write the statement. What this says, it says that let A be an n cross n matrix over C with eigenvalues. So you know that it is a n cross n matrix over C. So it will have n eigenvalues, exactly n eigenvalues. So let's say lambda 1 to lambda n, these are the eigenvalues. So with eigenvalues lambda 1 to lambda n in any given order, okay, any prescribed order. So you can, at the beginning itself, you can prescribe the order that you want to arrange these lambda 1 to lambda n in a particular order. So in a prescribed order. Then, depending on this order, then we can say that there exists a unitary matrix U of the same size such that U star AU is upper triangular. Not only that, upper triangular. So if you denote the entries of T as Tij, these are the upper triangular matrix. T is the upper triangular matrix, and these are the entries of upper triangular matrix T. Then you can say that there exists a unitary matrix U such that U star AU is equal to T, with the fact that the ith diagonal entry of T is equal to lambda I. That means you, whatever order you arrange these eigenvalues in, you can find U such that U star AU is equal to T such that the ith diagonal entry of T is equal to this lambda I. So this is for all I equal to 1 to n. So this is the statement of this result. Proof we will do in the next class. Now using this result, you can see that one can do many things. One important result or important advantage or application of this result is in the computation of computation of eigenvalues of a matrix. So you know what is done. So I'm just telling you this vaguely, some idea I'm giving. If you are still interested, if you are more interested, then you can Google it. So what it does in practice, as we have seen earlier also, as I mentioned earlier also, that if we have a matrix A and if the size of matrix is greater than equal to 5, then there is no way to find eigenvalues of A if A is A is a generic matrix. A doesn't have any particular structure. So if A is any matrix, randomly generated matrix A of size greater than equal to 5, then mathematician Abel, he proved that there is no way to find eigenvalues of A exactly, or you can say analytically. There is no way. So that means you cannot say that for any matrix of size greater than equal to 5, you can find its eigenvalues always analytically. For some cases, you can find if the matrix A has some particular structure, but in general, it is not. And therefore, finding eigenvalue, eigenvectors of a matrix is a difficult job in theory. You cannot do it. I mean, in theory, you can say that exist, but finding them is very difficult. And therefore, you need algorithms to find eigenvalues approximately. If not exactly, then approximately you find. And in those algorithms, so basically the QR algorithm is used to find eigenvalues. This algorithm is not known as QR algorithm to compute the eigenvalues of a given matrix A. A is of size n cross n. So what is the main idea of this algorithm? The main idea of this algorithm is that you apply similarity transformation on this A such a way, unitarily similarity transformation on this A such a way that this A becomes T. T is upper triangular. So you convert this A or you transform this A into an upper triangular matrix using unitarily similarity transformations. That means you apply iteratively multiply A with this unitary matrices Qi from left and right in such a way that it preserves the similarity transformation, and this after like ith iteration this matrix goes towards an upper triangular matrix. This iteratively you try to convert or transform this matrix A into an upper triangular matrix A. That means you try to make this lower triangular part as 0. Now you know that this similar matrices have the same eigenvalues, and therefore you can actually say, if you can achieve that, then you can say that the diagonal entries of this upper triangular matrix T, they are the eigenvalues of A. Now how it does that? It is actually in the QR algorithm. Why it is possible? It is possible because of the Schur's lemma. Schur's lemma says that you can always do that in theory, and this QR algorithm achieves that in practice iteratively. So it constructs these in this algorithm. You construct these QIs, these unitary matrices QI in a particular form using some idea from there is a way to choose these QIs. So you choose this QI in such a way that this matrix A becomes or A converts towards an upper triangular matrix, and this. So there are many advantage of. So you can say that okay, instead of QI, we already had a result which says that P inverse A, P is upper triangular. Then why did we use this unitary matrices here? It is because if you do it in this way, in theory you can do this way also, but in practice it is not a stable way, because computing inverse of a matrix is a difficult job, or it's a numerically unstable process. In theory it is fine, but in practice computing inverse of a matrix is a unstable method, is a numerically unstable process. Why? Because if how do we find this inverse of p? Inverse of p, we do some, like, we have some ways, like this Gaussian elimination also gives us a way to compute inverse of a matrix. And this is what in practice MATLAB does. If you in MATLAB, if you try to find inverse of a, then I think it uses this Gaussian elimination only to compute inverse of a given matrix. So that means you multiply, you use elementary matrices to transform your matrix A into an identity matrix, and that way you find inverse, right? So if you have A, then you multiply with elementary matrices in such a way that this A becomes, if A is identity, A is invertible, then the row reduced echelon form would be identity. So you try to find these E1 to Ek such that this becomes an identity, and using the, then if you can achieve that, then this product is basically the inverse, right? This is how it does. But as I mentioned, that finding this inverse numerically is an unstable process, because if suppose, let's say you have this diagonal matrix, let's say epsilon 0, 0, 1. Now for every epsilon greater than 0, this matrix is invertible, right? But what would be the inverse of this? Inverse of this would be 1 by epsilon 0, 1. Now if this epsilon is very small, is very small, that means if it's say it's 10 to the power, let's say minus 14, which is close to 0 in MATLAB, then dividing with a small quantity is introduce a lot of error. So this 1 by epsilon, this would be very large, of to the factor 10 to the power 14. So this would be very large. So this introduces error in your computation. And when you keep on using the same thing in your further part of your algorithm, then this error accumulate, and at some time you get result which is completely not acceptable. it it is not relevant to your original problem, and therefore you try to avoid computing inverse in your algorithm, because you don't know, although your matrix is close to singular, but MATLAB or in practice you treat this as a non-singular matrix because it is non-singular for every epsilon greater than 0. But if it is close to 0, then in practice, in theory it is still invertible, and therefore you compute the inverse, but the inverse you computed is actually has introduced a lot of error, because now this is close towards infinity, it goes towards infinity, because 1 by epsilon is close to 0, so this is close to infinity. So whatever computation you are making now, they are like they may lead to something which is completely like absurd. And therefore in place of P inverse, if you use P star, now if you know P, then finding P star is very easy, right? And there, that is the main advantage of having this unitarily similarity transformation, because the inverse is just now P star if P is unitary. So computing the main reason of getting towards instability can be avoided if you just choose this unitary. Not only that, you also know that unitary matrices preserve the length, also they preserve the angle. That means if x and y are two vectors, then you can verify that ux and uy, the length of ux and length of uy, they are same as length of x and length of y. That means they preserve the length. Not only that, they preserve the angle. That means x star y is same as ux star uy. So they also preserve the angle. The inner product is preserved. Here the length is preserved. So in unitary matrices also preserve length as well as angle. And whatever error is there in the algorithm, it is there. But in your computation, it is there. But using unitary matrices doesn't add any error in the process because of this fact here. They don't add any other error. So if the algorithm is is stable. It remains stable if you use unitary matrices in the process. But if your problem is a good problem and if you use inverse somewhere, then it may become unstable. Like you may get results which are not acceptable. I hope you understand what I mean. So that's why we actually need this Schur's lemma. It gives us a way to transform a matrix A into an upper triangular matrix, and it makes us possible to find eigenvalues of a given matrix. Okay, so if you're more interested in this, you can Google it, how to compute eigenvalues of a matrix, and then you will see that why this result is so powerful. Okay, so it's time. I already took your 7 minutes extra. I'm sorry for that. So we'll stop here, and in the next class, in the next lecture, we will prove this Schur's lemma. If you have anything, you can ask. Yeah.
So can you the classes of application based, can you take it down after the measure?
After major exam, yes, I can do that. Of course,
Yes,
that would be best. That would be good to all of us. I mean, especially to you, because you don't have to spend extra 2 hours before major exam. And since you are interested in knowing the application, we can do it just for learning purpose. I can take 2-3 lectures on applications. Yes, we can do that. That is
yes, sir.
it's a good idea.
And sir,
Thank you, sir.
what will be the syllabus for the major
Syllabus would
exam?
be everything, whatever we have covered in the course.
Okay, sir.
Sir,
Should be everything.
11 जो 11 तारीख को क्विज है उसका
11 को है या 10 को है? I don't remember the date. I will send a reminder today itself.
10 को है sir.
10th को है ना? So that would be the last quiz. There would be no more quiz even if you miss that or you have missed earlier, because it's too much work setting question paper and doing this. Also, if you miss this, then we'll see what we can do, but I won't take any extra quiz. I may take some oral exam, but that won't be good for you. So I would say that don't miss. If you have missed already any of the quiz so far, don't miss the next quiz. Also, if you have not scored well in the previous quizzes, try to score good in the next quiz so that your best 3 are considered. Yes, anything else?
So there was one question. Hello.
Yes.
So there was one question in when you are